Hi, this lesson is all about the risks that volcanoes can pose and how we can actually try and predict what those might be. Now, I've started um, this lesson with this image taken from the International Space Station. You can see we've got a fairly heavily populated area, but down in that large, round, dark spot, we have a volcano, Mount Vesuvius. A volcano that's dormant, but there's still magma underneath it. We even see a lesson from history with the destruction of the Roman town of Pompeii, which you can see just to the south of the volcano. Okay, there are two ways that we need to do this. The first is to look at the geography of these volcanoes. And for this, it would help to either have Google Earth or access to an atlas. If you haven't got Google Earth installed on your device, you can get it just by using a Chrome browser and searching for Google Earth. The geography of volcanoes is one of the first things that we need to look at in terms of the risk of volcanoes. I've given you an example of 4 different volcanoes from around the world: Vesuvius, Cotopaxi, Kilauea, and Mount Rainier. What I'd like you to do is I'd like you to find where each of these 4 volcanoes are, and then to estimate the potential loss of life that there may be if these volcanoes erupt. And you need to think about where these are in relation to population centres and also where they are in relation to plate boundaries. Now, if you look in your booklets on page 15, you'll find this table. And what I'd like you to do is I'd like you to have a go at filling this in. In the probable loss of life column, all I'm looking for is a descriptive term: high, medium, or low. Give reasons then for your answers. So press pause now and have a go at that activity on page 15. Okay, let's see what we've come up with. So this is the table we're working on. Let's start with Vesuvius. As we've already seen, Vesuvius has the potential to cause a large loss of life. And the reason for that is just how close it is to the second biggest city in Italy, Naples. The volcano itself is surrounded by millions of people. And we've seen from history the devastation that an eruption of Vesuvius could cause. Cotopaxi has a moderate risk to life. Now, the reason for that is, although a large city, Quito, the capital of Ecuador, isn't that far away, 50 kilometers for a volcano is a long way for anything really fatal to travel. Certainly ash could be a big problem in Cotopaxi, from Cotopaxi, particularly because it's on a destructive plate margin. But lava flows, pyroclastic flows, lateral blasts won't go 50 kilometers. Kilauea on Hawaii poses a very low risk to life. Now, although it's a very active volcano, it's not explosive. It slops out lava all the time. If you look at where Kilauea is on the big island of Hawaii, it's a long way from any populated area. There's some small villages around whose properties are at risk. We've seen that in fairly recent years. But in terms of loss of life, very low indeed. The final one is Mount Rainier. Now, Mount Rainier poses a very high risk to life. It's on a destructive plate margin, so it is explosive, and it's close to some very large population areas. We're going to look at Mount Rainier in more detail in a later lesson. So we can see that the location of a volcano, in terms of its plate tectonics and in terms of its geography, has a significant control on the risk that that volcano poses. But it's not the only thing that we need to be able to do to be able to assess risk. We also need to be able to predict a volcano, to understand what's actually going on, much as this geologist here is doing in the main crater of Kilauea on Hawaii. There's a number of different ways we do this. We're working here on the bottom of page 15 and also on page 16. Firstly, we can look at patterns of activity. This is Mount St. Helens' more detailed pattern of activity. We've already seen some evidence of this in a previous lesson. It sort of tells us that Mount St. Helens has dormant periods, 100 to 150 years, and then it starts to get more active again. But these things don't work on a bus timetable. We need to look at some other measurements from a volcano. One of the most useful is ground deformation. Volcanoes will swell up as magma rises to the surface. As magma sinks, they'll deflate, and that changes the shape of the ground at the surface. This is Kilauea in Hawaii. As the magma builds up, the sides of the volcano swell up and the angle of the slope increases. This is a diagram to show how this works. Can you fill in your copy of this graph to predict how each of the different stages would see a change in the width of the caldera at the volcano's summit? Stage 1 is where inflation starts to begin. Stage 2 is where it reaches its peak. The eruption happens, and then we have stage 3. If we fill in this graph, we can see a pattern that looks like that. That pattern will allow geologists to try to predict when that eruption could occur. It's not the only way in which we can predict a volcano. Gas emissions, for example, will increase as magma gets to the surface. We look for key gases like sulfur dioxide, carbon dioxide getting to the surface. One of the most important ways is earthquake activity, the seismic activity. We've seen that already underneath Mount St. Helens. We also see groundwater changes. Changes in the acidity of groundwater, changes in the gas in groundwater, changes in the level of groundwater. All of these are indicators of increasing activity. So, there are a number of different ways that we can use to try and predict increasing volcanic activity. All of them related to that movement of magma as we go from deep within the magma chamber as it gets to the surface. That magma forcing its way up will cause earthquakes. It pushes gas out. It makes the volcano swell up. All of these are indicators of magma on the move. Next time, we're going to be having a look at one of the most dangerous volcanoes, Mount Rainier. I'll see you then.